Good evening, everyone. A very warm welcome to all of you here in person and also those who are attending online. Thank you very much for your time, your interest, and for making yourself available this evening. I would like to extend my sincere thanks to the organizers RINA and IMarEST for giving me this opportunity. It's truly an honor for me to present on behalf of MAN Energy Solutions to such a distinguished audience at this prestigious event. Sir Isaac Newton, uh, arguably the greatest scientific mind to have ever lived, once said, "If I have seen further, it's by standing on the shoulders of giants." While I haven't seen any further like Newton, I am here today not because of my own qualifications or expertise, but because I stand with a giant in the maritime industry, MAN Energy Solutions. I would therefore like to thank MAN Energy Solutions Australia and especially our managing director, Mr. Jeffrey Moloney, who is present here this evening with us, for giving me this privilege. Now, allow me to briefly introduce myself. My name is Manulal Inasu. You can call me Manu. And I work with MAN Energy Solutions Australia as Sales Manager Marine. I'm responsible for new engine sales across Australia, New Zealand, and the Pacific Islands. I am a mechanical and marine engineer by training, and I also hold a master's in business management. I started my career 25 years ago as a marine engineer on board seagoing commercial vessels. And since then, I worked with several marine engineering companies, mainly engine builders, pump manufacturers, and cryogenic refrigeration system builders. With that introduction, let's now move on to the agenda for this evening. So here is the agenda for this evening. I will start with the origin and history of MAN Energy Solutions, including our association with Mr. Rudolf Diesel, the inventor of diesel engine. After that, I'll give an overview of the future fuel scenario in marine applications. Following this, I'll focus especially on our two-stroke ammonia engine development. Here I will discuss key technical aspects such as engine combustion characteristics, combustion stability, NOx emissions, ammonia emissions, nitrous oxide emissions, and fuel efficiency of our ammonia engine. Next, I'll move on to MAN's initiatives concerning future fuels in our four-stroke engine segment. Finally, we will conclude the session with a Q&A where I'll be happy to answer any questions you may have. If I'm unable to answer any question due to time limitations or because I don't have the information readily available, I'll be happy to follow up later via email or through the event organizers. So let's start with the rich history of MAN Energy Solutions. MAN traces its origin back to two German predecessor companies, the St. Anthony Iron Works in Oberhausen and the Sanders Machine Fabric in Augsburg. The St. Anthony Iron Works was founded way back in 1758, while Sanders Machine Fabric was established in Augsburg in 1840. So this remarkable legacy makes MAN Energy Solutions one of the oldest continuously operating companies in the world, with roots dating 267 years back to 1758. This slide is about the historic association between Mr. Rudolf Diesel, the inventor of diesel engine, and Machine Fabric Augsburg, which later became MAN Energy Solutions. The collaboration between Mr. Rudolf Diesel and Machine Fabric Augsburg began more than 130 years ago, resulting in the creation of the very first diesel engine. On this slide, you can see images of the original experimental engine built at Machine Fabric Augsburg, and also the patent certificate awarded to Mr. Diesel. Diesel's vision was groundbreaking. He initially designed his engine to run on vegetable oil, imagining it as a viable alternative to fossil fuels. He, of course, faced significant resistance from the fossil fuel industry, especially from the coal industry. So this kind of innovation often demands courage and foresight. And it was Hendrik von Buss, the general director of MAN at the time, who saw the enormous potential in Diesel's ideas. So MAN's unwavering financial and technical support was instrumental in bringing Diesel's revolutionary vision to life giving the world one of its most significant technological advancements, the diesel engine. So here is an interesting bit of history that might surprise you. When Rudolf Diesel demonstrated his engine at the 1900 Paris exposition, he didn't use petroleum-based fuel. He actually ran the engine on peanut oil. Yes, peanut oil. So Diesel believed that farmers can grow and produce their own sustainable fuel long before sustainability became the global concern it is today. It's fascinating how the very first vision for this engine was rooted in renewable and locally produced energy. Featured on this slide, you can also see a powerful quote from Rudolf Diesel himself. Let me read it out. The use of vegetable oils as engine fuels may seem insignificant today, but such oils may become, in the course of time, as important as petroleum. So when Rudolf Diesel said this more than a century ago, it might have sounded idealistic, but today it sounds prophetic. So as we gather today to discuss future fuels and confront the urgent need for sustainability and decarbonization, his words have taken a new and powerful meaning. What was once a distant possibility is now a pressing reality, and the shift he imagined is the very path we are now walking. It's a reminder that the innovation in fuel isn't new, and the seeds of today's transition were planted long ago. At MAN Energy Solutions, we proudly continue Rudolf Diesel's legacy, driving forward with an ongoing commitment to innovation and sustainability. Now, let's move on to the next topic on the agenda, which is an overview of future fuels. In this section, I'll share a few slides highlighting key global trends, including how the world population and seaborne trade are evolving. We will also explore what future fuel scenario looks like from MAN's perspective. Let's first take a step back and look at why this is important and what role we at MAN play in the decarbonization of the world trade and thereby contributing towards the sustainability goals set by UN. Today, nearly 90% of the global freight is transported by sea. The vast majority of this freight is carried by large ocean-going vessels powered by two-stroke engines. Out of approximately 33,000 vessels in operation globally, around 24,000 are equipped with MAN BMW two-stroke engines. In addition, there are roughly 12,000 MAN four-stroke propulsion engines currently in operation. So clearly, as a market leader, we feel an immense responsibility to drive this change towards decarbonization. We are committed to leading the technology development in marine propulsion. Most importantly, we ensure that this progress happens in the safest possible manner, which lies at the core of our development process. This slide shows two important graphs, the graphs of the world population and the corresponding increase in world seaborne trade. From 1990, 1990 until today, that's about 35 years, the world population has increased from approximately 5.5 billion people to 8 billion people we have on our planet today. Over the same period, global GDP has been increasing at a rate of 3% per year, causing the world trade, the trade by sea, to triple in size. Looking ahead, in the next 25 years until 2050, the population will increase by another 2 billion people. That's a current estimation. And this will continue to drive increased demand for energy, infrastructure, food, consumer goods, and more. And since the seaborne trade remains by far the most cost efficient and environmentally friendly way to transport goods, we expect that history will repeat itself and global trade will keep expanding. This slide shows the ambitious emission target set by IMO and the FuelEU Maritime Initiative plotted against time. In the previous slide, we discussed the growing trends in global population and seaborne trade. At the same time, something critical is happening that affects us all. That's global warming. So, in response, IMO, the International Maritime Organization, has translated the goals of the Paris Agreement into specific targets for maritime industry. So these targets were further strengthened in 2023 during the MEPC 80 meeting, and they are illustrated here clearly by the red line on the graph. So if you look at the red line, it clearly shows that compared to the baseline year of 2008, we must reduce the overall fleet's well-to-wake emissions by 20% by 2030, by 45% by 2035, by 70% by 2040, and then by approximately 85% close to 2045. And ultimately, by 2050, we should achieve 100% reduction. So the critical question is, how can we solve these challenging equations? Where the absolute demand for transportation continues to rise, while the targets for absolute emissions, then it's steadily becoming tougher to meet. So how do we solve that? That's the question. This slide shows the various fuel options available with MAN engines to achieve the decarbonization goal. We anticipate multiple decarbonization pathways to emerge as part of the future fuel mix. Many technologies are already available, with ammonia set to be the next in line. As you can see on the slide, we have already sold 187 methanol engines over the past 2 or 3 years. Most of these have been installed on large container ships, but a few of them on other vessel types as well. Additionally, we have the MEGI and MEGA engines for methane. Nearly 1,000 units of them are either in operation or in the order books. And for LPG, we have close to 200 engines in order or in operation. In the case of ethane, we have delivered around 63 engines, specifically designed for the ethane carriers. And after all these, and soon, we will introduce our ammonia engines. Altogether, more than 1,400 dual fuel engines are in operation or in the order book, and this number is continuing to grow. So clearly, there is significant change happening, and this transition is gaining momentum. So, what will the future fuel mix look like? In fact, this is the most important question facing our industry today. The one everyone is trying to predict, but it's not an easy question to answer, because the future fuel mix depends on many factors. And the reality is, many of these factors are currently unknown or still uncertain. Earlier, I showed you the IMO targets set at MEPC 80, but what I didn't mention was the so-called midterm measures, which will be approved in 2025 and are scheduled to come into effect by 2027. These midterm measures will significantly influence which future fuels become economically optimal. Of course, the optimal choice will also heavily depend on factors like ship type and size, and the readiness of the technology level, as well as operating expenditure, capital expenditure, and specific trading patterns. So all these factors will shape the future fuel decisions in shipping. Here is our prediction for the future fuel mix for the next 25 years. As mentioned earlier, many factors will influence this future fuel mix. Nevertheless, we have ventured to make a prediction extending all the way to 2050. with great uncertainty, of course. How did we approach this prediction? Well, up to 2030, it's somewhat easy because our order books are currently quite full. So we already have a good idea what the fuel mix is going to be for the coming years up to 2030. By 2030, we will still see significant use of fuel oil. That's a black portion on the graph, as well as a sizable share of LNG, which has steadily been adopted over recent years. You also see the gray area, which represents the methanol, clearly trending upwards. And there's a small bit of green on the top that represents ammonia, though it may be difficult to see here. I'm talking about the 2030, the bar for 2030. But how do we forecast beyond 2030? For this, we use very sophisticated models that examine every ship segment. We analyze the future requirements for bulk carriers, tankers, container ships, and others based on anticipated world trade growth. Then we assess how likely each segment is to adopt dual fuel solutions or alternative fuels. Combining these factors gives us the prediction illustrated here, supported by extensive underlying data and analysis. Yet it's important to stress this remains a prediction. The key takeaway, however, is clear. By 2050, we anticipate a diverse fuel mix. Now, if you look at the bar at the 2050, ammonia, indicated by the green area, is projected to become the largest fuel source. This is primarily because it currently offers the lowest predicted production cost and significant scalability. Methanol, shown in gray, also plays a crucial role, especially since it can reach near zero emission using electrolysis based hydrogen combined with biogenic CO2, carbon dioxide. However, the availability of biogenic CO2 might limit methanol's growth somewhat, but our prediction still places methanol at around 26%. LNG, or more precisely, methane, will also continue to play a substantial role. It's because it's established supply chain and wide availability make it a practical fuel choice, and it's capable of achieving around 20% greenhouse gas emissions reduction when used in diesel cycle in our MEGI engines, and even more if you use synthetic methane in the longer term. Finally, you still see the black portion there. The black portion represents fuel oil or bio oil. The reason is we are considering a 25 years average lifespan for the vessels for this calculation. So clearly, 2050 is just 25 years away from now. So vessels being ordered today will still be in operation in 2050, and thereby fuel oil remains a part of the mix. So here is the next point in our agenda, which is focus on two-stroke ammonia. Even though all the fuel options besides traditional fuel oil or diesel can be considered as future fuels for the maritime industry, from our perspective as an engine builder, most of these fuels are actually current fuels. This is because we already have engines successfully operating on these alternative fuel options today. So, as an engine builder, when I speak about future fuels, I would like to spend some more time discussing ammonia. Ammonia, from our perspective, truly represents a future fuel in every sense of that word. So, why is ammonia considered a relevant fuel? First and foremost, ammonia has the potential for zero tank to wake CO2 emissions, essentially covering scope 1 emissions for the ship owner and scope 2 emission for their direct customers. Additionally, uh, ammonia can achieve zero or near zero well to wake emissions if it's produced as green ammonia, which would also address scope 3 emissions for cargo owners. Another significant advantage of ammonia is that uh, it's already one of the most widely traded and transported chemicals globally. So there is already a well-established distribution infrastructure in place due to its use in fertilizers and other chemical industries. And the last point, ammonia also directly supports the emerging hydrogen economy. Now, what's the status of our ammonia engine development? Our colleagues in research and development have made tremendous progress in the recent years. I would like to quickly highlight some of their recent achievements. We have successfully run single cylinder tests on our research engine for a full year in our Copenhagen Research Center. 5 months ago, we initiated full-scale testing with our four-cylinder test engine. In January this year, we reached a significant milestone by achieving 100% engine load on ammonia with this test engine. In Japan, we recently saw the first commercial engine running successfully on ammonia. To provide some context, developing an ammonia engine is no small task, and we don't compare it to any previous engine development projects. Due to ammonia's characteristics, uh, especially its toxicity, attempting to fast track its adoption would be highly questionable. Therefore, we have adopted a very rigorous and careful development approach, which has also led to choose a market launch strategy that differs from other alternative fuels. Our ammonia engine journey started in 2019, over 6 years ago. Then we partnered with leading universities to study ammonia's combustion properties. And in 2020, we received our second test engine in Copenhagen. Throughout 2021 and 2022, we worked extensively on specifying the fuel auxiliary and safety systems, and engaged closely with the municipality and relevant authorities to secure all the necessary permits. Anyone who has visited our facility in Copenhagen knows there is a public school right across the street, which made it crucial for us to maintain a very transparent and thorough dialogue with the local authorities, especially regarding the safety. This careful preparation paid off, and in 2023 we had our first ammonia bunkering, and then successfully conducted our initial single cylinder tests. After running the single cylinder setup for more than 12 months, we rebuilt the engine in mid 2024 to prepare for full scale testing, which we began in November 2024. Since then, we have got excellent test results, which we are pleased and proud to share with you. So, MAN is announcing the start of a new reality for marine fuels. We can now openly say that ammonia as a marine fuel is indeed possible. Let's dive into some technical details that I hope you'll find interesting. Here you see our ammonia engine testing setup in Copenhagen. It's a 4-cylinder 50-bore engine capable of delivering 6,300 kilowatts at a maximum speed of 123 RPM. All four cylinders are operating on ammonia, and they are equipped with extensive instrumentation with about 1,000 measurement points that help us gather essential development data. The engine operates almost daily on ammonia, and we have already completed hundreds of hours of testing across many operational scenarios. In the following slides, I'll share some of the test results and general conditions which give us confidence that we have made significant progress in ammonia engine development. We will begin by looking at the combustion characteristics across the engine as a whole. When the engine is running on ammonia, you can see here on the left side, we observe compression, combustion, and expansion curves very similar to other dual fuel engines. This consistent behavior is seen across various engine loads, shown here in a comparison with diesel and methanol. This is very positive results, indicating efficient ammonia combustion comparable to diesel and methanol engines, with all engines tuned to the same maximum pressure Pmax level. Moving to the next slide, we will look at combustion stability in terms of cylinder to cylinder variation. So what you are seeing here is a graph showing pressure variation inside each of the four cylinders while the engine is running on ammonia at around 75% load. Now, although there are four curves on this graph, one for each cylinder, you might only see one single curve. That's because the pressure traces from all four cylinders match so closely that they are practically indistinguishable. This is a really strong indicator of combustion stability and balance across the engine. And that level of precision is made possible by our advanced engine control software, which ensures consistent combustion performance in every cylinder. Next, let's examine combustion stability from cycle to cycle variation or process stability over time. Here, we clearly see similar pressure deviations for ammonia compared to diesel, which is impressive given the fundamental difference between a hydrocarbon fuel and a nitrogen-hydrogen based fuel like ammonia. Even at a high load condition of around 75%, we observe negligible deviations, confirming the robustness and stability of our ammonia engine. In this graph, the red curve represents nominal propeller curve. The green ellipses represent various load conditions from 25% to 100%, and the yellow ellipse is the low load operation. We have thoroughly evaluated the engine not only at the nominal propeller curve, but also at heavy running conditions and light running conditions. At each load point in the green ellipses, you can see heavy and light conditions on either sides of the propeller curve. So we use a water brake setup in the test facility, and then we can simulate these light and heavy running conditions. So our tests under these realistic sailing conditions show remarkable stability of the ammonia engine. These tests also enable us to confidently state that shaft generators or PTO power takeoff solutions can be applied with our ammonia engines, just like in the case of other dual fuel engines. Now, regarding emissions, it's clear from the data presented here that when operating on ammonia, we achieve approximately 40 to 50% reduction in NOx emissions. These results are from our research engine in Copenhagen. But however, we can confidently state that our final production engine will comply with Tier 2 and Tier 3 emission standards, and the later with the aid of SCR catalyst. The SCR catalyst will always remain active, effectively reducing NOx emissions. The SCR is not only needed for the NOx, it's also needed to neutralize the ammonia slip. So our aim is to have ammonia slip uh, just slightly below the NOx levels, and therefore they will cancel each other in the presence of a catalyst. On the subject of ammonia slip, I would like to highlight our advanced injection technologies, which significantly influence ammonia slip characteristics. We are currently testing multiple injection methods and aiming for the optimal balance between ammonia slip and NOx emissions. Uh, Although the legislative targets for ammonia slip are not yet finalized, our internal goal remains ambitious, aiming for a very low ammonia slip level. Now, I would like to share some important findings about nitrous oxide or laughing gas, which is a highly potent greenhouse gas with around 300 times the global warming potential of CO2. Extensive testing and measurements show nitrous oxide emissions from our ammonia engine are extremely low, typically below 5 ppm, which translates to a greenhouse gas impact of less than 2%. To put this in perspective, our ammonia engine achieves over 90% reduction in total greenhouse gas emissions compared to a traditional diesel engine. This is really an impressive achievement by our R&D team. Here, let's take a look at the fuel efficiency. Our testing so far has shown that the thermal efficiency of ammonia in our ME LGI engine is very close to that of diesel. Now, these results are from our test engine in Copenhagen. While the final commercial engines may have slightly different tuning, the efficiency will remain in the same range. Each fuel, diesel or ammonia, will have its own optimized engine settings to get the best performance. Although you might see some small differences later on, the overall picture is clear. Ammonia has the potential to match diesel in terms of thermal efficiency. So even when accounting for factors like ammonia's evaporation energy, our measurements show that the overall efficiency levels out thanks to the higher combustion efficiency observed in the research engine. This slide shows a few points about the pilot fuel oil consumption. Regarding pilot oil consumption, we have confirmed our R&D target of 5% pilot oil consumption at full engine load for a L1 rated engine. This aligns with other dual fuel engines like a methanol dual fuel engine. And when it comes to fuel oil mode, we have already seen identical engine performance as a conventional fuel engine. I would like to mention a few points on cylinder and piston ring conditions observed in our ammonia test engine. Both the single cylinder tests running for over a year now and the ongoing full scale engine test show excellent component conditions. Uh, we are using the proven 3-ring pack configuration from our other dual fuel engines. This is performing exceptionally well, showing minimal wear and virtually no deposits, mainly due to the low carbon content in the combustion process. We have been successfully using BN40 category 2 cylinder oil and will recommend this for commercial applications. There were countless scavenging space inspections on the test engine. No ammonia has been found on pistons or other components. We have never detected ammonia odors or alarm triggering levels of ammonia, confirming our system is completely gas tight. I hope that throughout this presentation, you have been able to sense just how excited and proud we are of what has been achieved, both by our engineering team and our R&D colleagues. The progress made so far gives us great deal of confidence in ammonia as a marine fuel and the role that amine energy solutions will play in its future adoption. I would like to take a moment now to talk about our market introduction plan for the ammonia engine. We are currently involved in several pilot projects. We have chosen this phased approach deliberately before going for a full sales release because we want to make sure that the introduction of ammonia as a marine fuel happens in a safe and controlled way. We want to gain a real world seagoing operational experience that's positive and safe before we fully open up for commercial sales. The exact timing will naturally depend on shipyard schedules and the finalization of international rules and regulations related to ammonia as a fuel. But our best estimate for a full sales release of the ammonia engine for our G50, S60, G60, G70, and G80 engine platforms is around the fourth quarter of 2026. The pilot projects we are engaged in include very large ammonia carriers, large bulk carriers, and pure car and truck carriers. And we are also in discussions for the first ammonia fueled container vessel. I'm happy to mention one of these pilot projects. This is the first signed contract for a ME-LGIA engine, ammonia engine, and it's with our long-standing partner, Eastern Pacific Shipping. They will be building two very large ammonia carriers at HD Hyundai Heavy Industries in Ulsan. The engine for these vessels will be a 6 G60 MEC LGIA, and we expect the first engine to be delivered at around January or February 2026. This engine will then be handed over to the shipyard for further construction of the ship. We are deeply involved in this project and feel very encouraged by the strong collaboration with Eastern Pacific Shipping, Hyundai Shipyard, and our licensee partner at Hyundai. So we are definitely moving in the right direction and, more importantly, at the right pace. To summarize, based on the very promising results from more than 300 test runs on both the single cylinder and four cylinder setups, we believe ammonia will play a key role in the multi-fuel future of shipping. We are aiming for a full commercial release by the end of 2026, but that will be based on successful seagoing experience. Our engine development work is progressing in parallel with the finalization of rules and regulatory framework. And we think it's the right decision to wait for that regulatory clarity before launching on a full commercial scale. Just to be very clear, we do not want to fast track this rollout. The nature of ammonia, particularly its toxicity, requires a very careful and responsible approach. So, while we fully support the global push for a rapid decarbonization, uh, we believe it's critical to do it the right way. That principle, doing it right, is absolutely central to everything we are doing in this project. So the next topic in the agenda is future fuels in four-stroke engines. Earlier, I discussed in detail the steps we are taking with the two-stroke engines to prepare for alternative fuels. Since we are nearing the end of presentation and I want to stay within the allotted time, I won't be going into the same level of detail here. Instead, I'll just give you a quick overview of our four-stroke fuel initiatives to give you a sense of the directions we are heading in. The approach is tailored to the four-stroke segment, but the overall objective remains the same, supporting the industry's transition towards cleaner fuels. So here you can see the three main future fuels that we are focusing on: methanol, ammonia, and hydrogen. We are actually working on all three options, although we are at different stages of development for each one. The progress depends largely on the market demand and the priorities we have set based on our in-depth analysis of the future fuel landscape. Because of the larger size and scale of our two-stroke engines, it's relatively easier to conduct experimental trials on two-stroke engines. But the good news is many of these insights and the results from those trials can be applied to our four-stroke engines as well. This slide gives an overview of the energy density differences between various marine fuels and what that means in terms of storage space on board a vessel. As you can see, future fuels like methanol, ammonia, LNG, and especially hydrogen have much lower energy density compared to the conventional diesel. So, excuse me. To illustrate this, the chart compares how much volume is needed to store the same amount of energy across different fuel types. So we are taking diesel as a reference here. So diesel requires the least space with 1,000 cubic meters needed for a standard reference energy content. In comparison, methanol requires about 1.6 times that of diesel. I mean, 1.6 times more volume than diesel. Ammonia needs roughly 2.4 times more volume, and LNG about 2.8 times under specific temperature and pressure conditions. When we look at hydrogen, the difference becomes even more dramatic. Liquid hydrogen needs around 7.2 times, and compressed hydrogen, depending on at what pressure it's compressed. If it's 350 bar, it needs 14.3 times, and if it's 700 bar, it needs 8.3 times. The gray area in the bars also show additional space required due to the cylindrical shape of the cryogenic or high pressure tanks, which adds to the overall volume needed on board. So one of the key challenges with adopting alternative fuels is not just the engine technology, but also accommodating the much larger fuel storage systems within the limited space available on board ships. This slide shows the three different types of injection technologies possible for alternative fuels in four-stroke engines. Each of these is suited to different fuels depending on the combustion characteristics and technical requirements. The middle one, that's a low pressure port fuel injection, which follows the Otto cycle. It's the simplest to implement and also the easiest to retrofit. So it's often the starting point. However, it comes with some limitations. For example, in methanol application, only up to 70% of the fuel can be methanol, with the rest still needing to be diesel. This method can also be used for hydrogen, but again, only in small quantities, up to 25% by volume. The left one is high pressure direct injection, which works on the diesel cycle. This is essential for ammonia, since ammonia has a very poor ignition characteristics and burns quite slowly. So high pressure direct injection can also be used for methanol and allows much higher substitution ratios, up to 95%, while offering better efficiency. The third one on the right is low pressure direct injection, which again follows the Otto cycle. This setup is ideal for hydrogen. So as you can see, there is no one size fit all solution when it comes to injection systems for future fuels. There is no one size fits all solution. The choice depends on the range of factors like market needs, customer preferences, regulatory frameworks, and the technical capabilities of each fuel. That's why we spent considerable time and resources analyzing different scenarios and speaking with customers before finalizing our development roadmap. This slide gives a comparative overview of the feasibility of using methanol, ammonia, and hydrogen as future fuels in four-stroke engines. The table is color-coded to indicate increasing levels of feasibility, from red being the least feasible to green being the most. It considers a range of factors, including fuel properties, safety, availability, and price. As a general conclusion, methanol currently appears to be the most realistic option in the short to medium term. That said, the best choice of fuel also depends heavily on the specific ship type and its operational profile. In this slide, you can see MAN four-stroke methanol engine roadmap as of early 2025. It outlines both retrofit availability and new engine deliveries across different engine platforms, giving a clear picture of how MAN is progressing with methanol solutions. On the retrofit side, we can see that several engines are already being prepared for conversion to methanol, including the 2131DE 4860 common rail and 3244 common rail. On the new build side, you can see methanol ready certified, which means they are built with future conversion in mind. The 175D is another important platform. It's our state-of-the-art high-speed engine, and it's planned for both retrofit capability and full dual fuel methanol operation as a new build option. The key takeaway here is that MAN is taking a strategic and phased approach, prioritizing both retrofit solutions for existing fleets and new engine platforms with built-in methanol readiness. This approach gives ship owners flexibility whether they want to act now or prepare for a future switch depending on fuel availability and regulatory developments. Here we see an overview of the key engine modifications required when adapting our engines to run on future fuels. As we shift to fuels like methanol, ammonia, hydrogen, several parts of the engine need to be adapted or upgraded. Starting with fuel injection system, since these fuels, as I explained earlier, have lower energy density, we often need a higher mass flow, which means using larger injection systems or additional injectors. That in turn affects the cylinder head design because we need to make room for the extra injectors. Ceilings is another critical area. Methanol and ammonia are quite aggressive, so only certain materials can handle a long-term exposure to these fuels. The fuel piping may also need to be replaced or upgraded. Stainless steel, for example, is required in hydrogen applications. On the piston side, changes are normally or mostly relevant for diesel engines during retrofitting, and not typically for dual fuel engines like LNG diesel. We also need to update the engine electronics to manage the new combustion parameters, and we need to install the upgraded control systems. In addition, adapted safety systems are essential. Things like double-walled pipes, drainage systems, and fuel leak detectors all become part of the setup. Finally, to meet IMO Tier 3 emissions, we may need to integrate exhaust after-treatment systems like SCR for NOx reduction. And of course, beyond the engine itself, the onboard fuel supply system also need to be adapted accordingly. This slide explains the concept of retrofitting existing engines to run as a dual fuel engines using methanol port fuel injection or PFI. In this setup, methanol is injected into the intake ports, while diesel acts as the pilot fuel for ignition, following a pre-mixed auto combustion process. One of the biggest advantages of this concept is that it's a relatively easy retrofit solution for existing engines without requiring major redesigns. The methanol fuel supply and onboard systems are simple and robust, avoiding the need for complex high-pressure equipment. It also allows for a high share of methanol in engine operation, and when combined with biodiesel, the engine can run in a fully carbon neutral mode. This system is designed to be flexible, so operators can switch between diesel and methanol depending on availability or operating conditions. Another key benefit is that the conversion can be done progressively during planned maintenance stops by installing methanol-ready parts in place of standard service parts. So, thanks to this modular design, it's even possible to carry out the retrofit at sea, which helps minimize the downtime and disruption of the vessel operations. This slide covers the concept of retrofitting an engine to a high pressure direct injection or HPDI dual fuel system for methanol. In this setup, methanol is directly injected at high pressure into the combustion chamber, following a diesel combustion principle, with diesel acting as the ignition source. This concept is already proven in two-stroke engines and offers a reliable path forward for four-stroke engines as well. This system is optimized to enable very high methanol share across the full engine load range, and when combined with minimal biodiesel, it can operate in a fully carbon neutral mode. A major advantage here is the emission performance because of the cleaner combustion process. There may be less need for exhaust after treatment systems. Just like the port fuel injection concept, this system also offers operational flexibility, allowing a switch between methanol and diesel depending on the fuel availability or operational requirements. Um, what I explained in the PFI concept, here also the retrofit process is modular. So during routine maintenance stops, methanol-ready parts can be installed in place of standard ones to prepare the engine step by step. And thanks to this modular nature, the full engine conversion can also be carried out at sea, making it practical and cost-effective for the operators. This slide highlights some of the key considerations when retrofitting a diesel engine for dual fuel methanol operation. The retrofit can be done on both conventional and common rail base engine. The retrofitted engine is assumed to be able to operate at 100% MCR in diesel mode. The retrofit package will have methanol port fuel injection system integrated into the intake manifold, along with a complete methanol fuel train supplying the engine. To support this, certain design modifications are needed to accommodate the new fuel injection equipment. It will also have the updated engine automation, combustion control, and safety systems to handle methanol operation. Methanol specific safety systems such as draining systems, purging systems, double wall piping, and leak detection sensors. These are critical components of the retrofit. The entire retrofit solution will go through a type approval test, which is done in close cooperation with the relevant classification society. Um, the existing plant requires to have a methanol supply system operating at 10 bar with the required flow rate, and depending on the classification requirements, exhaust after treatment may be needed. Finally, a plant-wide safety concept must be developed and aligned with the classification society to ensure compliance and operational safety. So with that, this presentation comes to an end. Once again, I sincerely thank you all for being here this evening and for patiently listening to what I know has been a rather long presentation. While preparing for this talk, the real challenge was not to find the relevant material about future fuels. In fact, MAN has a lot of information about future fuels. The real challenge was actually filtering that information to make sure the presentation stayed within the time I was given. So when we talk about marine future fuels, the amount of data, the number of variables, the contributing factors, and the uncertainties are just enormous. So trying to present all of that in a limited time frame is honestly quite difficult. This means that I had to skip several topics, and in some areas I may not have gone into as much details as you would have liked. So, but you can see my email address on this slide, and I warmly welcome you to reach out if you have any questions or if there is anything I can assist you with. I will do my best to get back to you with the information you need. And now let's move on to the Q&A.